Hi everyone, I'm very glad to be part of this event. It's first time for me to speak in a virtual conference. I'm very excited, and many thanks to the fantastic organizer for making this happen. I am Paolo Mainardi. I am the CTO and founder of an Italian company based in Milan. We do cloud-native development, Kubernetes consultancy on different aspects, building custom operator and also on-prem installations. And if you want to know more about us, you can check out our website. There are a lot of information there, some case study and so on. For any questions regarding this talk and more, please feel free to contact me. What I want to share with you today are the following topics. I will be very quick. I have a lot of things to show you, but keep all the questions for the end of this talk. And I will start with what is the hype cycle of emerging technologies and why it's important to know it. I consider this point very important because the technologies we adopt to build or improve our business have an impact on us for years. So we should choose it very carefully. Then I will review the serverless concept like function as a service, backend as a service, and so on. Then we'll talk about how to implement serverless-kind workloads or computing model on Kubernetes. So the hype cycle is a branded graphical presentation developed by Gartner to represent the maturity, adoption, and social application of emerging technologies through 5 main phases. So actually we can use this tool because it's a tool to better understand the market and according to our confidence on risks, choose or not to invest in a technology. The very first phase of this tool is the technology trigger. The technology trigger is where a potential disruptive technology is conceptualized. Most of the time it's just a proof of concept and nothing is really proven. And if you use Docker as an example, it was the 2013 when Docker was presented for the first time at the world at PyCon with a lightning talk of just 5 minutes titled The Future of Linux Containers. At the time Docker was much more than a CLI to run Linux containers, a wrapper around LXC, which is a Linux technology. And you know what happened next. In just 5 minutes the talk basically changed everything. Now when this happens, a lot of interest gets generated around the technology and the product thanks to the spreading of news and contents through the social media and the conferences. We face the peak of inflated expectations, where we are in this stage we are over the early adoptions. The early publicity produced a number of success stories, but also a lot of failure ones, and the negative press led us to the trough of disillusionment. In this phase, the curve of the hype cycle begins to descend until comes a point where the media start to abandon the topic and also the adopters start to leave the products. This happens most of the time because the adopters and the enterprises feel that the technology does really fulfill the hype or is not capable to absorb what initially promised. So for the surviving company, there is the slope of enlightenment, where more instances of how the technology can benefit the enterprise start to crystallize and become more widely understood. This is also a phase where second or third generation products start to appear from technology providers. We can think about the last iteration of Docker Swarm, using a Docker analogy again. And the last phase is the plateau of productivity. In this phase, the technology is widely implemented and mainstream adopted. We can think about the Kubernetes containers today. Its place in the market, its applications are well understood, and the standards and criteria are really defined to evaluate technology partners. So where is placed serverless inside this hype cycle trend? And the last report we have from Gartner is from 2017, was placed between the technology trigger and the peak of inflated expectations. It's totally correct to me at the time because it was not really yet a mature technology. but now I think that we are over the we already reached the slope of enlightenment. There are a lot of serverless products. The investments are growing. Adoptions of serverless technology is widely accepted, also for enterprise workloads. So, to me, it's totally safe today to choose to implement some of our workloads of our new generation application to extend our business using this kind of computing model. According to Gartner, in the next 3 years, serverless will become the predominant cloud computing model. So, what is serverless and which technologies are we talking about? One of the criticisms or jokes about the name is that the end servers are still needed to run our code, but okay, if we look at this from another perspective, we can compare it to the term wireless, where we take it for granted that the cables are still needed to connect my router to the network, but me as a client, I can just use it without attaching a cable to my phone or my laptop to use it. This is the very same paradigm. Servers are still needed to run the code, but me as a developer or as an operator, I don't have to care anymore about provisioning, maintaining or planning the infrastructure. I can just focus on my code and shipping very fast to the cloud. So according to the CNCF definition, serverless computing refers to a concept of building and running applications that do not require serverless management. As I have already said, it means that operations engineers are still needed to run the infrastructure, to run the code, but those infrastructure are completely abstracted away from the developers and IT operations team. Basically, we describe a new finer-grained deployment model where the applications are bundled as one or more functions and uploaded to a platform. Then this platform will take care to execute, scale, and bill me in response of exact demand needed at that moment. So, a serverless computing platform usually provides one of both of those categories of services, the function as a service or just Faas, which provides this event-driven computing platform, and the backend as a service, which are third-party APIs based services like database, authentication platforms, queue system, and so on. And as those API are provided as a service, they can auto-scale like the functions, and they operate transparently, and they are built like in the same way the functions are built in a pay-as-you-go billing model, so they appear totally to developers to be serverless. So serverless is all about the developer experience. As Kelsey Tower said one time, when we have a great idea, the last thing we want to do is set up the infrastructure. I agree totally with this. I think that building software is an act of creativity and should be sustained in all the ways possible. And also everything that can help me to reduce the time to market and help me to deliver business values quickly is just pure gold. So serverless is all about the developer experience because of these 3 key points of serverless, which is cost and resource efficiency can scale down to 0. It's based on a pay-as-you-go billing model that can scale up on demand, and its automation mechanism of scaling, failure handling, and recovery. So let's start to focus now on function as a service, one of the major innovations of the serverless ecosystem in the last years. I will explain what serverless functions are by using a real-world business scenario. An example of development of a cloud-native product considering both parts, coding and cloud architecture. So let's imagine that we have been asked by our business department or by one of our customers to implement something to translate text files coming up from different sources, from Italian to German, and they also provide us a list of non-functional requirements. They want a system capable to scale up on demand, which is highly available to respect their SLA because it's very critical. It must be capable to scale down to 0, and finally they want a pay-per-use billing model. So we do a couple of meetings with our DevOps engineering team. We agree on the following stack. We choose Node.js as our development platform, and as a hosting platform, cloud platform, we choose GCP for its cloud services and for their Translate API. So we start to develop the application, which is very simple. It's a very short code base. It's like 15 lines of code, and basically what we define is HTTP endpoint using the Node.js Express framework, where we receive the data to translate. Then we use the GCP services to translate the text to give back to the user, and to store this translation in object storage bucket. So the application is ready to be deployed, and now the development part is done. We start to look at the ways to ship it into the cloud according to the non-functional requirements. It's very tough because the non-functional requirements are complex to achieve all the ones. So we decide to use an iterative approach. We start by defining a very simple architecture, which is based on HTTP global load balancer, a virtual machine running our code on a region, just one zone of this region, in this case B. But of course we fail of our requirements because we cannot scale up. We are not HA, and at the end we have also fixed costs just to run the services. So we iterate again. We can add an instance group so we can scale from 1 to n, but all the rest is still failing. So we work a bit more on the HA aspects. So we propose to add new zones to these regions, to use all the zones available, and so we spin up the virtual machines with the instance groups on A, B, and C. And now the infrastructure is much more reliable. We have our HA requirement green, but the rest is red again, because we cannot scale down to 0, and we cannot do it just using traditional hardware services. Sorry. And finally, we already have the pay-as-you-go red, because we have the fixed costs that now are more than twice as before. So we have to wait now. We can invent our custom solution to try to accomplish all the requirements, or we try another approach. So we know that the GCP offers a serverless platform, so we decide to investigate on that. We know that according to the GCP function documentation, it's very simple to expose a Node.js application on the wild on HTTP. And we just need this very simple refactoring. We strip out the Express web server and management, because it will be handled by GCP, and we are done. We don't need to change anything else, and we are ready to deploy this function on this GCP function service. So this is how the new architecture looks like. It's much more simple than before. As you can see, we don't have any other moving parts other than our function and the external services. And all the non-functional requirements are now green. We can scale up on demand. We are HA. We can scale down to 0. We have a billing model, pay as you go, and we don't have anymore any fixed cost. And in addition, we no longer have to deal with managing the infrastructure, because basically we don't have any infrastructure to manage here. We have our application running on the cloud, and everyone is happy. So the key properties of Faas, as we saw, basically the functions are much like the functions we use to write the conventional applications. They are small, separate units of logic. They are stateless and ephemeral. This is one of the most important properties, because as we are not in control of the underlying server infrastructure, we can, for example, save a file to disk on one run and then expect to find that file on the next run, because all the invocations can virtually be executed on different servers. and they are designed to spin up very quickly, do their work, and then gets destroyed. They are also designed to have a maximum execution time according to the vendor imposed limits that goes to seconds to a few minutes depending on the vendor. Then it's scalable by default from 0 to n, and as they can scale to 0, they are affected by a phenomenon called the cold start, which is the time the cloud vendor spend to allocate the resources to spin up the function on a machine, on a server, and then make it available to the external world. You can think the time we spend when downloading a Docker container before we can make profit of it. It's not very much different than that. Then the functions are event triggered. That can be invoked by HTTP, which is an event, or all the other events available on the cloud service, like the database, authentication, and so on. We can attach the functions on all these kind of events. And finally, they are fully managed by a third party. Once I deploy the function, I don't need to invest any other time to maintain functions. I just can use it. Everything is in charge of the cloud vendor. So the state of Faas on the public cloud, it's in a very good shape, but there are some little quirks to here and there to keep in mind to take better decisions. The very first one to me is the limited language runtime support. For example, if we are deploying, if we want to deploy something using a very niche language like, I don't know, Erlang, I cannot actually run it on a standard serverless runtime because they tend to support the most used language like Python, Node, Java, .NET, etc. Then we are also forced to use some sort of vendor proprietary mechanism to package and deploy the functions. We cannot rely on containers. We have just to take our source code, use their command line, and push it on the cloud vendors. But we can use any kind of standard like the OCI, for example. Another two big problems I see are the locked-in language runtimes, which means that I cannot extend or modify the runtime that we run my functions. But some vendors like AWS allows to do this using the layers, but generally speaking you can't. The other one, the biggest one to me, is the format of the event interchange between the cloud services, which is most of the time a proprietary format, which also lands us into the Lockin arena. So let's see what really is the Lockin. I will use again a real-world business scenario for this. Imagine that we already have an application capable to convert CSV file to JSON just using GCP services. It's working smoothly, it's already in production, and we have been asked by our business department to extend it also to other vendors. In this case, we want to support the same stream of data with the same kind of services, but on Amazon AWS. So we wire up the things together. We configure SQS to push the messages on our cloud function, but the function broke. So let's see why. Because the event format, as you can see on the left and the right side, we have the messages coming from the two vendors. On the left side we have AWS, and on the right side the GCP. The kind of service, it's the same, pub, sub, and SQS, but the format is totally proprietary. So one of the things we can do to solve this problem is building something like an event processor before hitting our function. Maybe it could be another function or just an extension of our function. And we should also invent our custom standard format for messages to manage. I don't know, maybe tomorrow I will need to extend another provider. I need a way to define a standard message format, but I don't need to invent my standard because I can just use Cloud Events. Cloud Events, it's a specification from the CNCF. It's a joint effort from the serverless working group of CNCF with the goal of standardize the event data in a common way. It reached the stable version just some months ago. And currently Cloud Events, even though it's been contributed by the public cloud vendors, it's not very widespread adopted, and it's just supported by Azure natively. I almost sure that in one way or another providers will eventually support this model, even though the things are moving slowly than expected. So before digging more on the serverless concept applied to Kubernetes, I want to be sure that every one of us have the share the same overview of what Kubernetes is. It's a system to manage containers in a cluster, has been created by Google based on an internal project called Borg. And as we can see here on this diagram, Kubernetes is composed by different components, and all the components we see here defines what we call the control plane. The control plane is a set of processes that on the right side run on the master, on the left side run on the master nodes, on the right side on the worker nodes, and the most important is the kubelet. It's an agent that runs on each node of the cluster to make sure that containers are running in a pod. And then we have the pods that are grouped on one or more containers with shared storage network and specification to run it. So why do we want to run serverless kind workloads on Kubernetes? Let's see how is the developer experience now on Kubernetes. We have to write the code, we have to build a Docker image, we have to push the Docker image to a registry, we have to write a lot of YAML manifest, and knowing also all the APIs around this manifest to deploy our application, like the service, deployment, the ingress. And then we have to apply it to ship our application. But what we want to do is to write the code and ship it, as we can do with serverless. So developing on Kubernetes is not very easy. It's not the right abstractions for end developer experience, because there is much complexity to tackle. But it's a great platform to build a platform as a service on top of it. So let's imagine that we want to build a serverless development experience on Kubernetes. So we will need something to wake up workloads, something to scale up and scale back to zero, something to turn the source code into a container, and an eventing system with the configurable sources and subscriber. We can choose to use Knative. Knative is a Google project, open source Google project. It's a Kubernetes-based platform to build, deploy, and manage modern serverless workloads. As I said, it's a project by Google, but has been contributed a lot from most of the big vendors like Pivotal, Red Hat, IBM, and so on, and offers all the features we saw earlier of a modern serverless platform. So the building blocks of Knative are Kubernetes at the bottom, plus service mesh, and we have the primitives that are three big components. They are three different projects. There is the Knative serving, Knative eventing, and finally Knative build. Knative serving is the crucial part of the system. It allows to scale up and scale back to zero our applications. It's basically what defines our application as a serverless function. And thanks to the use of the service mesh, it allows to have a fine-grained traffic routing, to have automatic metrics and telemetry coming up from the services. And one of the most important features is the point-in-time snapshot of code configuration that creates the revisions that we can use to do advanced deployment like Canary, or to do A/B testing of our new functions to the end users. This is how we define a new service, a new function on top of Knative, and as you can see, this very simple manifest abstract away all the complexity of Kubernetes, because we are defining a Knative service where we define our containers, some configurations, and basically is all we need to do to deploy an application on Kubernetes. If you know Kubernetes a bit, you know that to express these kind of things, we should use at least a deployment manifest, which is much more complex than this, a service, and an ingress. Then we have the Knative eventing component. This is a complete eventing system, very complex under the hood, but very easy to use. Very complete eventing system for event-driven apps. And it's composed by two components, which are the broker, which is the components which receive all the events from the channels, external channels like pub/sub messages and so on, and the trigger, which is the components which connects the broker to our application, basically. And of course, it's everything. All the messages are based on a cloud event spec. This is how we define a trigger. We are connecting the broker with the subscribers. The subscribers are our services. And as you can see from this very simple example, the messages coming up in and out from the broker and the trigger are just Cloud Native events messages. Then there was the Knative build components, but has been deprecated in favor of Tekton pipelines, which is a new project started by the Knative build source code. And this project provides all the primitives to declare, to create CI/CD style pipelines using Kubernetes resources. It can build the Docker image, the containers, we're using a lot of different systems like building Canic or BuildKit to build the images totally inside the Kubernetes without external dependencies like Docker, or just using standard formats like Bitbugs. And it's openly governed under the new foundation, which is the CDF, which is a new branch of the CNCF. So what we can do, we can Knative as a developer, we can use it directly to deploy our stuff in a more streamlined way than raw Kubernetes. As an operator, I can use it to put a level of abstraction between Kubernetes and devs. And as a platform architect, I can use Knative as my framework to build my own Paas, relying on the Knative primitives. Let's see some of the Knative native platforms out there in the market. The most production one is the Google CloudRun. It's a fully Knative service. It's of course an event-driven architecture. It's a mix of container as a service and managed cloud Knative installation, because it exists in two versions. There is CloudRun for Anthos that allows me to deploy fully managed, sort of managed Knative plus system on my cluster, or I can just rely on CloudRun, which is a sort of container. It's a container as a service platform, and it exposes a Knative sort API based on not on Kubernetes but on the Google infrastructure. You can find more information on the link at the bottom of this slide. Then there are other two platforms, the one from Red Hat, OpenShift Serverless, which became GA just some months ago, and it's used all the Knative components. And then another one that it's worth mentioning, it's Pivotal Reef, which use some of the Knative components apart the builder part, which is based on a custom builder. There are of course other Kubernetes native platforms which are not based on Knative but just on the Kubernetes API like Knative. I will show you some of them. The first one I want to show you is KEDA, that it's acronym for Kubernetes Event-Driven Autoscaling. And unlike Knative, this is a project that not aim to cover all the aspects of a serverless platform, but just a specific part, which is the event-driven computing model. It's an open source CNCF sandbox project from Microsoft and Red Hat, and it's basically made of three components. The first one is the custom metric server for the Kubernetes HPA. The second one is the KEDA controller, which loops inside the cluster on the scaled objects, which are the objects that connect the external events to the metric server. and it's in charge of scaling from 0 to 1 or vice versa, and from 1 to n instead remains in charge of the standard HPA. Basically, it covers just what Kubernetes doesn't do now. Then there are the scalers, which are the connection with the external world, with the external services, that so all the services capable to emit events, that with KIDA we can use it to spin up or spin down the services. And basically what the controller uses for managing the scaling part. Then there are other platforms, more simple and smaller platforms than Knative or KEDA, that I collected here in a list. The most popular one, like Kubelet from Bitnami, Faas, and Apache OpenWhisk, Fission, and etc. And they share some common aspects, like they are open source, they are very flexible in terms of language runtimes. They have also a custom CLI to manage the entire life cycle of the platform, which is very important for serverless platforms, because when I want to build my source code into a container, I don't want to deal with a lot of things. I just want to do everything from one command line. And they are written in Go, so if you are an expert, Go expert, you can easily extend it. It's the same language of Kubernetes, of course. And most of them, Apache OpenWhisk is implemented in Scala, and usually they are backed by big vendors. This is a plus, because when the project is backed by big vendors, it's more unusual that can disappear from one day to another. Another very interesting project that should be mentioned here is Virtual Kubelet. It's an open source Kubernetes kubelet implementation that masquerades as a real kubelet. This allows and opens the doors to introduce inside your standard Kubernetes cluster an infinite capacity, computing capacity that cloud vendors offers. So we go back to the Kubernetes cluster diagram, we see that we have the nodes with the kubelet running, but we can replace it, or we can add another new virtual node using the virtual kubelet, that for Kubernetes will be just the other nodes, but this one just registers itself as a node, but on the underlying APIs, it's using external services like Azure Container Services, for example, like AWS Fargate, Alibaba Cloud ACI, or HashiCorp Nomad, or you can implement your own custom provider. This is very cool because basically we don't need to change anything on our app. We can just deploy our pods on the infrastructure, and for Kubernetes, the real node and the virtual ones will be basically the same. We add infinite scalability capacity on our cluster. Of course, there are some quirks, but it's a very promising project. So, serverless on Kubernetes has a lot of benefits, because we can be much more flexible than standard serverless runtime. We can deploy containers instead, just rely on runtimes. We can run it on a multi-hybrid cloud and on my laptop, and if I have some strict requirements based on policies on my workloads, and I cannot deploy the workloads on serverless platforms, I can have as well on my Kubernetes cluster the same benefits of serverless computing model on using Kubernetes on my hybrid or private cloud. I can mix and match stateless and stateful workloads. This is another of the benefits of using Kubernetes, and I can, of course, extend as much as I want because I'm using Kubernetes, and I introduce a better development experience for the Kubernetes developers. One of the advice I have for you to finish is to use this CNCF serverless landscape to understand, to monitor the new services, new tools, new frameworks that finish under the umbrella of serverless platforms. And to finish, I really think that in some point in the future, the serverless computing model will be the predominant one on Kubernetes, and we will be able to ask to Kubernetes to just run the code as we can do with the serverless platforms, with all the benefits of using Kubernetes. That's all. Thanks a lot for your attention. I hope you have enjoyed this presentation, and for any questions, I'm available on the channel. Thank you so much, guys.